S of B minus S of A over B minus A. That's average velocity. Okay, and Grant said if we did V of B minus V of A over B minus A, something that many people will do on the next test when I ask for average velocity, they're going to do this, but Grant says don't do that because that's finding average what, Grant? Acceleration. Okay. Nice. Can you say it again, Sarah? That was really great. Average velocity is that. And Catalina, what would average acceleration be then graphically? What would average acceleration be graphically? This is true. No. Sarah, can you say average velocity one more time? Because Catalina's going to listen to it and she's going to be able to figure out how to change your sentence and make it the average acceleration. No. Okay. On V of t, it's the slope on velocity that we're finding for average acceleration. So when she said her sentence, average velocity is the slope of the secant between 2 points on S of t, I thought you'd change it to say average acceleration is the slope of the secant between 2 points on V of t. So you just had to change S of t to V of t. Okay? Any questions about that? Or that? It's the secant for both, because remember, a secant line is a line that connects 2 points on a curve. Secant connects 2 points on a curve. So when we're talking about average velocity between A and B, we're looking at S of t, we're going between those 2 points, and we're looking for the slope of that secant line. Now, Catalina just mentioned tangent line. What does tangent line to S of t at a point tell us, Dylan? Good. Which would be what if we were talking about the slope of position at a certain time? That would be instantaneous velocity, right? So the slope of the tangent at a point is on S of t is instantaneous velocity. Okay. Yeah, please.
Is that tangent at all related to sine over cosine tangent?
Yes, and I'll let you discover how. Because you've made a connection and I don't want to spoil it.
No, I said it. It's not connected.
Oh, they're connected. Okay. How do we compute instantaneous velocity? We have Stephanie's not preferred method of wicked close points. Don't want to do that. Yesterday I showed you if you happen to have a velocity function, you could plug a number into it, and it would poop out the velocity at that point. Yeah. So that's great if I have a velocity function. But if I have not a velocity function, but only a position function, that's my question. What do I do if I'm given position and I want to find instantaneous velocity? That's going to be our topic for today. But first, I need someone with two fists. Gender is not an issue. Come, stand, present your fists that we might discuss the space between them. Okay, I want you all individually to imagine a continuous function between a comma f of a and b comma f of b. Who saw this function? Who saw this function? Did anyone see this function? I saw that. Any function you want, as long as it's don't let them down. That's okay. Between this point and this point. The intermediate value theorem says, and this is going to be one of our very, very important terms, and we'll come back to it a number of times. On a closed interval from a to b with a continuous function f of x, doesn't matter what the shape of it is as long as it's continuous between those 2 points, the function must pass through every y value between that y value and that y value. So let's say I got this one. I'm going to pass through all these y values. Let's say I drew this function. Oh, it doesn't matter because I'm still going to pass through all these y values. I don't know anything about these y values. But I know, according to the intermediate value theorem, that I have to pass through all the y values from this one to this one. Now, how could that be useful to me? Well, let's imagine this is a negative y value, and this is a positive y value. What must exist somewhere between this x value and this x value? A 0. This is a way I can find x-intercepts. And to find x-intercepts, I set the function equal to 0. That's going to be the way you see this, and I can guarantee an intermediate value theorem question on the AP exam. Okay? We will come back to this a couple more times. But it came up in last night's homework? Yeah. Yeah, it did. Yeah, it did. Which one?
The last one.
Oh, that was my question.
Kaylee. Good job. And I'll need those fists again. Okay. Number 51. 51 says, explain why e to the negative x equals e to the x has at least one solution. E to the negative x equals e to the x. Now, some people say, well, Mr. Goodler, that's kind of obvious because you taught me how to graph years ago. I know e to the negative x looks like this. I know e to the y equals x looks like this, and I can see one point of intersection. And that doesn't demonstrate any calculus knowledge on my behalf. So instead, we're going to talk about IVT. And we said that IVT is between any 2 points, provided I have a continuous function, I have to pass through all the y values from this y value to this y value. Now my function could look like this. My function could look like this. It doesn't matter what my continuous function between these points looks like. As long as a, the function, is continuous, I know that I have to pass through all the y values from this y value to this y value. Look, all the y values get covered, all of them, regardless of which colored continuous function I'm talking about. I'm going to pass through all the y values from this one to this one. So if we say, hey, one of those values is negative and one of those values is positive, then we can use IVT to identify a 0 of the function. But that requires me to have a function equal to 0 to find the x-intercepts of. So instead of doing this, I'm going to subtract x from both sides, and I'm going to say e to the minus x equals 0. Aha! So let's put in something on either side of where we thought graphically that point of intersection would be. Do we think the point of intersection is in negative land? How about at 0? So I'm going to put in a 0 for my left side, and I don't know where that is, so I'm a little scared. Well, 1, 2, 2, 3. Let's see what happens. So if I plug in a 0, I get e to the 0 minus 0 equals, and that's 1 minus 0 or 1. Uh-oh, that's positive. Oh, that's positive. Ooh, all right, so I need something on the other side? The other side is just going to be more positive. Did I draw the graph wrong?
That's right. But if you subtract e to the negative x to the other side,
Yeah.
then when you put in the 0, you get a negative 1.
Oh, but why doesn't this work? Shouldn't it work both ways? Okay. I agree with you. If I subtracted this from both sides and made the 0 here, I'd have negative 1. Well, let's put in something further over, like f of 2. So, oh, that's going to be minus 2. Okay, so e to the negative 2 minus 2. Well, I know e to the negative 2 is 1 over e squared, minus 2 is definitely less than 0. So on one end, I'm less than 0. On the other end, I'm greater than 0. And so I know that somewhere in between 0 and 2, there must be an x-intercept according to the intermediate value theorem. So that's what I'm going to say there. I don't have to get any closer. It's not asking me where is this x-intercept. It's just saying show that there must be one. So I would write since f of x equals e to the x, e to the negative x minus x is continuous on 0 to 2, and f of 0 equals 1, and f of 2 equals 1 over e squared minus 2, comma, according to IVT, the intermediate value theorem, there must be at least one point when f of x equals 0 on 0 to 2. And that's actually the kind of justification that we need to write unless we respond to the AP. Which is one of the reasons we practice writing sentences all the time. Any questions about that statement or about that question? Yeah.
So when the y value switches from negative to positive, positive to negative, that means that there's no section.
No, y has to equal 0 in there. Yeah. Johnny, a question?
I have confused losses.
With what part?
All
Do you remember her fists? So we're saying that if we have a continuous function between her fists, regardless of what that continuous function looks like, we're going to pass through all the y values from this y value to this y value. I don't know anything about these y values. I don't know anything about these y values. But from this y value to this y value, on a continuous function, I know I'm going to pass through all the y values in between. Okay so far? All right. So then what happens if we show that at one side, one of the fists is below the x-axis, and at the other side, that fist is above the x-axis? If I'm going to pass through all the y values in between, one of those y values would be y equals 0. So this is a way for me to guarantee or to note there's an x-intercept between this x value and this x value. When, as Ben said, my y values go from negative to positive or from positive to negative on that interval. So then down here, I said, okay, let's create a situation, e to the minus x minus x. We're wondering when this would be equal to 0, because that would be a point where e to the minus x equals x, point's an intersection for those other curves. And so I looked on either side of where I thought there might be an x-intercept, and I noticed on one side, I got a positive value. And on the other side, I got this 1 over e squared, which is a tiny number less than 1, minus 2, and that's going to be a negative number. So I'm negative on this side, I'm positive on this side. Therefore, somewhere in between positive 1 and 1 over e squared minus 2, I'm going to pass through y equals 0. So there is at least one place where the function f of x equals e to the x minus x will equal 0. And that's the justification sentence for it. That's when they say, show that this is so. I write these words. This past year, actually, there was a huge discussion, I guess is a polite way to put it. It used to be that you didn't have to include this. Yeah. You could just say, according to IDT. But they said, no, we're changing that. You have to explicitly mention that the function is continuous. You need to address the precondition of IDT. I have a continuous function between 2 points. Okay. Anything else? Anything else from the homework you want to talk about? Yes, Nick. 37. Verify the function is continuous and state its domain, indicate which of the theorems you're using, and which of the functions you're assuming to be continuous. Well, I kind of want to say theorem 7, because I've got a function inside of a function. And I know x plus 2 is always continuous. But I can't have anything less than negative 2. Oh, that's not a problem. Because remember, the domain of that inside function, square root of x plus 2, this one has a domain of negative 2 to infinity. And I know that whatever this poops out is going to be a number. If I plug in a negative 2 here, I get 0. The lowest y value that this poops out, 0. I can't have 0. I can't have 1 over. That's a great question. What did you come up with? It wouldn't be continuous from, say it again, please. So I'm told properties. Theorem 6, quotient property. If the functions f and g are continuous at x equals c, then the following combinations are continuous at x equals c, and one of them is f over g. So I'm using theorem 6, the quotient theorem. Okay, yes. Oh, good job. Thanks for reading the book. Okay. Since I didn't know what it was, do you think you're going to be tested on that? Good job. Okay, cool. Let's move on. I want to talk about this, how do I find a slope at a point in a way that doesn't make Stephanie want to throw rocks at me. So, here's what I want to imagine. I want to imagine I have 2 points. The first one is called x, f of x. Then I'm going to go over a bit. Let's call that amount h. So this new point would be called x plus h. This ordered pair, therefore, would be x plus h, comma, f of x plus h. So then Stephanie says, that's still 2 points, Mr. Cooper. Yes, it is. What would the slope be between these 2 points, Stephanie? Which we could simplify to be f of x plus h minus f of x all over h. That's a slope formula. Anyone remember seeing that before? Yeah, we saw that last year in chapter 1. We called it the difference quotient. It's called the difference quotient because look, there's a difference, and look, there's a quotient. Okay, this is the difference quotient. Stephanie says this is a slope formula between 2 points. But Stephanie also says, Mr. Kukla, it's still 2 points. So what do I need to do calculusly to make this point be that point? Yes, please. No. A point. I need tangent line. I need to get this point to be that point through some sort of calculus magic. Yes. I can't just assign h to refer to something perhaps we've learned in the last week in chapter 2. A limit, maybe? So now what we're saying is, sure, there are these 2 points, but we want the limit as this point slides down on top of that. That's what this tells me. And this, then, is my limit definition of the derivative. There are actually 3 limit definitions of the derivative. But I think Darity wants to see how this one works before I move on to the other 2. Sure. Darity, I'm going to use a simple function because it's a Wednesday. Okay. Let's say I want to know f prime of 3. That means I want to know the slope of f of x at x equals 3 without using 2 wicked close together points. I'm going to pick a simple Wednesday f of x. Okay? Now, here's my difference quotient. I know that f prime of x equals f of x plus h minus f of x over h. This is a recipe. Find f of x plus h, find f of x, subtract them, divide by h. How do I find f of x plus h? No. That's one of the other 2 definitions. We'll get there. Darity, how would I find f of 2? I put 2 in for all the x's of f of x. How would I find f of 3? I plug 3 in for all the x's of f of x. How would I find f of triangle? Good. How would I find f of small puppy? Great. So how am I going to find f of x plus h? You said that, didn't you? You said that, right? And so now I'm asking you this question. No free. This doesn't say f of 3. This says f of x plus h. You take what's ever in there, whether it's a small puppy, a triangle, or the number 2, and you plug that stuff in for all the x's of f of x. Not just some of the x's, but all the x's of f of x. Okay. So then, we know then that f of x plus h will be x plus h squared, or x squared plus 2xh plus h squared. Please don't forget the FOIL here. This middle term is crucial. It's not x squared plus h squared. That's cool noodle. Okay, so step 1, Darity, was find f of x plus h. Remember, step 2 was find f of x. Yeah, I plug in for x for all the x's of f of x. Great, and that's what I end up with. So f of x equals x squared. What am I supposed to do with these two things that I found? I subtract them. If all of f of x doesn't cancel out every single time, you've made a mistake somewhere. These cancel, and I'm left with the limit as h approaches 0 of 2xh plus h squared over h. What now? I can factor out an h's, because if I plug in 0 now and do direct substitution, I get 0 over 0 in indeterminate form. So instead, Morgan says, hey, do some more algebra on that. Factor out an h on top, 2x plus h over h, and cancel those. Now can I plug in my 0? Heck yeah, and I end up with 2x. Hey, and I don't know if you remember from the microscope worksheet, but 2x was what we grabbed as the f prime graph for y equals x squared. So this is f prime of x. But what was I trying to find, Darity? No, I was trying to find the slope of f at 3. Not just f prime of x, but f prime of x at 3. Now, plug the 3 in for all the x's of... I can't hear you. Which function? Don't say of the function, because look, I got two different functions here. I don't know which one you're talking about. No. No, that doesn't tell me the slope of f at 3. That tells me the y value of f at 3. What did we go through all this work for to find f prime of x, if not to use f prime of x? Look, it says f prime of 3. Plug a 3 into f prime. Okay, so if f prime of x is 2x, then I've got 2 times 3, or 6. This, f prime of x, is the general slope machine. I can plug in any x value, and it will poop out slopes for this parabola. I build this when I want to find the slope at more than one point. But we have some single-use limit definitions of the derivative. If one of these is called f prime of x, and that's the limit as h heads to 0 of f of x plus h minus f of x over h, and that finds the slope machine, f prime of x, we also have two methods for finding slope at a point. Let's call that point x equals a. One of those methods is I now have a specific x value. I said that I want to do this at x equal to a. So any place I saw an x, I replace it with an a. So that limit definition would be f prime of a. The slope at that point will be the limit as h heads to 0 of f of a plus h minus f of a over h. because this now represents some specific number. And Darity's going to go through another example with us, but this time using this limit definition of the derivative at that point. Here, it was general derivative. And now I've built this machine over here, and I can just throw x values into it all day and get slopes at different points. When I'm done with this, I'm just going to have a number, and that number represents the slope at that x value on f of x. Yes?
So once you find the slope machine, would like a problem ask at a certain point what's the slope?
Like this problem said, what's the slope at 3? Okay. Hey, Darity. So our f of x is still x squared. And our a value is 3. Because I want to know the slope of f of x at 3. By the way, we should end up with 6 when we're done. Hope so. Okay. So this says f of a plus h, but my specific x value is 3. So I plug a 3 in here, and I plug a 3 in here. And so now this looks like this. F prime of 3 equals the limit as h approaches 0. And yes, you have to write the limit every time until you do the direct substitution. F of 3 plus h minus f of 3 over h. Hey, look at the difference quotient again. How do I find f of 3? And for all the of f, there's no prime here. This is still algebra 1. Hey, how do I find f of 3? For all the, great. How am I going to find f of 3 plus h? For all the, right. So f of 3 plus h will be 3 plus h squared, or 9 plus 6h plus h squared. And how did you say I would find f of 3? So f of 3 will be 3 squared, or 9. What am I supposed to do with those two things that I found? I subtract them. What should always happen? This thing should always disappear completely. Behold, it did. And so now I've got f prime of 3 equals 6h plus h squared all over h. Hey, Mr. Cooper, where's your limit definition? I don't know. H approaches 0. Okay, Morgan wants to say, take out an h, because otherwise if you do direct substitution, you get 0 over 0. So this is going to be the limit as h heads to 0 of h6 plus h over h. These cancel. Can we do direct substitution now? Yes, we can. And we get 6 plus 0, or, Darity, are we happy? Yes, we get the slope at 3 is 6. But notice, all this does is tell me the slope at 3. If suddenly Megan comes over and says, oh no, I didn't want it at 3, I wanted it at 2, we have to repeat the whole process. If I had gone through and I built the slope machine, she says 2, oh great, we just plug a 2 in now. This is a multi-use tool. This is a single-use tool. But why would I use that, Mr. Cooper? Oh, just don't worry. There'll be a reason for it, and I'll let you know. Okay, next. Stephanie, I got another way of looking at the slope at a point that's different from the drawing we did here. And as soon as I take Johnny's question, I'm going to draw that one up. Yes?
Why do you put the h in the denominator, like, after you cancel out the 9?
Because it was always there.
Yeah, what is h?
Stephanie answered my question about 10 minutes ago when I said, hey Stephanie, how would you write the slope between these 2 points, x, f of x, and this other point here, x plus h, comma, f of x plus h? And she said it would look like this,
Oh, okay.
and then the x's would cancel and we'd have an h in the denominator. And do you see now, Stephanie, how amazingly cool it is that this 0 over 0 limit that we've been talking about recently suddenly is the foundation of differential calculus? This is the calculus magic that allows me to find the slope at a point, and therefore find instantaneous velocity as opposed to average velocities, or even wicked close together average velocities. This finally is slope at a point. That's what that does for me. Okay, so I promised you a second picture, Stephanie, and here's the second picture. I've got a curve, and this curve is called y equals f of x. And I've got some point here on this curve called x, comma, f of x, because that's what the curve is. But here's the place where I want to find the slope. And so let's call this x equal to a. Well, Garrity tells me the y value at that point would then be, if this is the x value, and you want to know the y value, I plug in an a for all the x's of f of x to find the y value at that point. Okay. So I've got these two ordered curves. Okay. So now what I want to do is I want to take this point and slide it down so it sits on top of that point. Can you write me the slope formula for this situation? Good. And what's my limit? My limit, there's no h's in this picture, Darity. That's why I was looking at you funny. I have to say x approaches a. I want to slide this point down until it sits on top of that point. So there's my limit definition of the derivative, and this is a second f prime of a. So let's go through and use it again. The same f of x, the same f prime of 3. We already know the answer is 6, but let's show it using this other definition. So if I want f prime of 3, I'm talking about the limit as x approaches 3 of f of x minus f of 3 over x minus 3. Any questions about the setup? Yes? Pause.
Why isn't that the average slope formula?
Yes, it is. Until I do what? Until I make there be no distance between the 2 points. I agree that if I'm looking at f of x minus f of a over x minus a, that that's the slope between 2 points. But if I put this in front of it, now I'm saying, take this point here, x, f of x, and slide it down the curve until x approaches a. So this point will come to sit on top of that point. And when this point sits on top of that point, this is no longer a slope between 2 different points. This is now a slope at a point. It really is calculus magic. Yeah. Good. Chew on that for a while. This is section 2.4. It's our first encounter with the limit definition of the derivative. Don't worry. Even when we're done with the chapter 2 test, 3.1, we're doing more of this. So this is going to be with us for a little while. Okay, and then, Stephanie, because you're going to be tired of using the limit definition of the derivative to find the slope, like you were tired of wicked close together points, then we'll bust out the real shortcuts. Okay? But first we have to understand the conceptual underpinnings of what the heck we're doing. So let's finish this one up quick before that bell rings. How do I find f of 3, Darity? Good. So 3 squared is 9 over x minus 3. Hey, look, if I put a 3 in, I get 0 over 0. Uh-oh, I better use my algebra skills to rewrite this. X approaches 3 of x minus 3, x plus 3 over x minus 3. And those cancel, and now I plug in my 3, and I get 3 plus 3, or 6, is f prime of 3. And so now I have the slope at a point. Now I have the instantaneous rate of change. And you'll see some of this in your homework tonight, and we'll be doing a lot more of this tomorrow. Oh my God! How did you do that? They all just realized that I didn't get the CFA today. Huh. Well, I know what we're starting with tomorrow. CFA tomorrow, and then more of this. All right. Bye now, and then we'll review for the test.